So I've told you what the coefficients mean in terms of the the slope, how they modify this prediction function. I've told you how to get inference in them, but who cares? How do you actually interpret this stuff in any kind of meaningful way? So the first thing we'll talk about is descriptive interpretation of logistic regression, which again, this is going to mirror the linear regression part. This is generally what people do. They look at all the coefficients and then they wave their hands about what this means. It's also probably the useless and least meaningful of the ways that you can interpret logistic regression. But let's see what's going on, right? So we already talked about this. Bigger coefficients mean more impact on predicted probability. So if you have this bigger coefficient, these things are changing more steeply, more dramatically. And if you have the negative coefficients, then the change is going in the opposite direction. So at a minimum, you can say if you have a big coefficient, this predictor is changing the predictions very dramatically. Okay, either increasing the risk dramatically or decreasing the risk dramatically. But it's predicted risk. It's not necessarily real risk. This is what the model thinks. Okay. So let's dig into it a little bit more. The linear predictor is what we call, in terms of interpretation, what is it? What do I mean when I'm say it's changing the risk? Like in what way is it changing the risk? So the linear predictor, this thing here, is the log odds of the predicted probability. What I mean by that is exactly this, what I have written here. So if I have here this p hat, this is my predicted probability at a given point x. And we know that that's the sigmoid function, the logistic function, where the input to the logistic function is the output of this linear function. To get from here to here, it's just algebra. So I can show you what I did here. So I'm going to move this term over to the other side, this denominator over to the other side. So I have 1 over the p hat, and then I'm going to subtract the 1 from that. So it's going to be 1 over p hat minus 1. So then what's left over on the other side is just this. So I can take the log of that to get just this negative linear predictor. And then I have the minus of that to get rid of the minus. So now I just have this on the other side, on the other side of this. And it turns out these two things are the same because I can multiply so I can have it as p hat over p hat. 1 over p hat minus the 1 is the same as p hat over p hat. So that's, and then minus log of that. 1 minus p hat over p hat. And then the log of a ratio is the difference of logs, and then the minus. Basically, I can flip these two things around, and so I end up with this. Now, okay, so I have some relationship between what that describes the predicted probability as a function of this, what I'm calling the linear predictor. What is this? This is what we call the log odds. So p hat over 1 minus p hat. This is, so think of this as the predicted probability of the outcome, right? So probability of the outcome given x. And then this one is 1 minus that, which is the same as the probability that y equals 0 given x. So this thing, probability y equals 1 over probability y equals 0, is called the odds of something happening. So higher odds means things are tending more towards y equals 1. Lower odds means things are tending more towards y equals 0. It's just a particular way of looking at something. Not necessarily the most interpretable. And then here we have the log of that. So that is the relationship we have here. So if we concretely want to interpret this coefficient, we can say that this slope is the amount that the predicted log odds, which is this thing over here, increases if we increase this predictor by 1 unit. Okay? And then similarly, beta 0, the intercept, is the predicted log odds, assuming that this predictor is set to 0. Okay? And so let's keep thinking about this. Notice that this odds it's a function of x, right? So here I've just written p hat 1 over p hat. I'm just going to write this thing p hat over 1 minus p hat as q. And notice that q depends on what x is, right? Because over here, this is a function of x. So I'm just writing this explicitly using this parenthetical notation to say, okay, q is a function of x. So this log odds is equal to this, this linear function. So let's think about now what happens if I have a binary predictor. So little x only takes the values 1 or 0. So for example, if little x is a treatment indicator of whether somebody got a drug or placebo, or little x is, as in that problem that we were doing before, indicator of whether somebody got fresh blood or older blood in their transfusion, any kind of binary predictor. What happens here? So the log odds were evaluated at x equals 1. So here I've written q1. What happens here, I just get beta 0 plus 1 times beta. And for q0, I just have beta 0 plus 0 times beta. So if I solve for beta here, so obviously this term is gone. So let's just take the difference of these two. So if I have log of q1 minus log of q0, the difference, these betas will cancel, and then we just get is equal to beta, right? And the difference of two logs is the same as the log of that ratio. So I get that beta is equal to log of q1 over q0, and remember this thing is the odds at x equals 1, and then this one down here is the odds at x equals 0. So it's the ratio of two odds, which now, let's write that out very explicitly. We can see here. So on the top, we have the odds at x equals 1. On the bottom, we have the odds at x equals 0. And we have that this coefficient is the log of that odds ratio. So this is the standard interpretation of the coefficient for binary. For a binary predictor, people just say, hey, the coefficient is just that log odds ratio. So if you want the odds ratio, you just need to exponentiate the coefficient, e to the beta, and that gives you the odds ratio for this predictor. Call it a day, right? If there are additional predictors, you get a conditional odds ratio. So here, let's say x2 goes in here as well. Then the thing is, you have to interpret. So here we have this q of 1 at an x2. So this is the odds at x1 equals 1 and x2 equals little x2. And this is the odds at x1 equals 0 and x2 equals little x2. If you do the same thing, you'll see this stuff cancels. But your interpretation of this has to be the ratio of these two odds. In other words, the odds are fixing the value of x2. So it's conditional at x2 equals a particular value. And the interesting thing is, okay, well, you might think, but no matter what the value of x2 is, if I take the difference of these two things, this term cancels, right? So condition on x2, this log odds, it's always the same number, right? Like let's say this number is 10, right? If I condition on x2 equals 5, that number is 10. If I condition on x2 equals 12, that number is 10. It doesn't matter, right? So does the conditioning actually do anything? Shouldn't it, can I just drop that out and say that this conditional log odds or conditional odds ratio, given this value of x2, is just the odds ratio? This what we call the marginal odds ratio? And it turns out the answer is no, which is very strange and counterintuitive. But even if it's constant, the definition of this conditional odds ratio depends on what other covariates are in the model. So this is very strange. It takes a minute to wrap your head around. So here, let's set up a data generating process where we have x1 and x2. These are both binary variables, and I've set y up to be. So here I'm actually following an actual logistic regression model. The coefficients are, the intercept is -1, the coefficients are 1 and 1. Okay. And I just sample a very, very large data set, so call it a population, and I'll compute the population marginal odds ratio. So the way I do that is I just take the mean of y in the subpopulation where x equals 1, and yeah, this is just essentially this formula down here. So this is the marginal odds ratio. We've seen this before when we talked about S-demands. the population marginal odds ratio. Now here what I'm doing is getting the conditional odds ratio. So I've grouped first by the value of x2. So I've computed this odds ratio in the group of people for whom x2 is 1, and then also in the group of people for whom x2 equals 0. And so I'm actually going to get two numbers there, but they're actually both going to be the same number, and that's what I have here. And then down here, I've done logistic regression on the entire population. So there's no sampling variability or anything. It's the whole population. And I've taken the coefficient for x1 and I've exponentiated. And these are the results. So there's no sampling error here. It's not like this logistic regression coefficient is not an estimate of the odds, is just randomly off a little bit from the odds ratio, because I'm using the whole population. It's just that this thing is not the same. It is not an estimate of the marginal odds ratio. It is estimating this conditional odds ratio. And that's very weird, okay? And this conditional odds ratio is not the same as the marginal odds ratio. It's bigger, right? And so if you did this analysis, if you had a large data set, you're not worried about sampling variability or inference or anything, and you thought, hey, the effect of this treatment or whatever is 2.7. Well, actually, it's not. It's 2.5, right? This is just it's a different estimand, and this estimand actually depends on what other coefficients you have in the model. So it's very strange. It's not really a good thing to go after. This is kind of a weird thing, and it's unique to this odds ratio. It's not unique to the odds ratio, but it's not every estimand is like that. So risk difference, for example, which is much more interpretable than odds ratio because you're not taking a ratio of ratios. So risk difference is very clear. It's just what's the probability in this case minus the probability in that case. Very simple, right? If it's positive, then it's higher risk. If it's negative, then there's lower risk. For risk difference, let's do the same kind of thing. So I have the same data generating process, and now here I'm computing the population marginal risk difference. It's just the probability of y in the population of people who have x1 equal 1, and the probability of y in the subpopulation where people don't have that. And here what I'm doing is the same thing, except first I group by x2. So I compute that in the two subgroups. And then in here you see the number I get is actually the same. And this is the case even if the risk difference actually varies in the population. So here I'm making it so that there's a different risk difference in the x2 group, in the x2 equals 1 group, than in the x2 equals 0 group. So there's two subpopulations where there's two different risk differences. And I can get these numbers to match up by just averaging the risk difference in those two populations. And it turns out that the average of the risk difference in those two populations is the risk difference in the total population. Now that's kind of what you want, what you would want, but that is exactly what is not the case for the odds ratio. So the average of the odds ratio of the marginal odds ratio in two different subpopulations is not the same as the marginal odds ratio in the total population. And in fact, this number, it depends on how you split the subpopulation, the number that you get. So what you're conditioning on, which is very, very strange and makes the whole thing completely not interpretable. In my opinion. So this phenomenon is called collapsibility or non-collapsibility. And you don't really need to understand all of the details here. The main takeaway is that the odds ratio is, in particular the odds ratio that you get from logistic regression, if you're trying to interpret the coefficient as an odds ratio, is not the marginal odds ratio. And the marginal odds ratio is already a little difficult to interpret relative to a risk ratio or a risk difference. And then you're compounding that difficulty by now saying, actually, it's not even the marginal odds ratio, it's this conditional odds ratio, which is the thing that depends on what other covariates I have in the model. Like the estimand is changed by what I'm adjusting for. So it's just an absolute mess, honestly. So here is another example where we have, here I have three independent variables, x1, x2, x3, which are all binary. And then I have my outcome. If I run the logistic regression, again, this is population data, so there's no sampling variability or anything like that. If I run the logistic regression with all of these, this is the predicted conditional log odds ratio. Okay, that's how I can interpret this coefficient. If I take away one of these conditioning variables, and these are independent, so it's not like they're collinear. In the linear regression case, we saw that if you have independent variables, they're not collinear. You can add one in, take one out, and it's not really going to change the coefficients of the other things in the model because you're not kind of soaking up the effect, because those things are not explaining the same kind of variance in the outcome. But here's a case where these variables are actually totally not collinear, and just taking one in or taking one out is changing this coefficient. And that's because you have this nonlinearity, so things behave a little bit differently. But then if you're going to interpret this as an odds ratio, it's very strange, because the value that you're getting just depends. And again, this is the true value. This is like the estimand in this case, because we have population data. The estimand depends on what else you have put in the model, which makes it very uninterpretable. Okay, so what the fuck? Message here again. Interpreting linear regression coefficients, we know that's already difficult, because even there, the estimand, right, depends on what else in the model. You're asking about an increase, 1 unit increase in something, given that we've fixed everything else at particular values. Here you have that same thing going on, right? You have that conditioning, given that you fixed everything else, 1 unit increase in this is that. How does that impact the log odds? But especially if if you don't understand the difference between the marginal and the conditional log odds, it makes it very, very difficult to pin down what these coefficients are actually supposed to mean, even in a descriptive sense. And so the really final takeaway here is that this common practice of just exponentiate all the coefficients and calling them odds ratios, that's usually quite bad. And what about inference? So we haven't really talked about confidence intervals and all of that stuff. Well, everything just carries over from linear regression. So things that you want to watch out for. Testing, you can say, oh, there's no significant effect, therefore this predictor doesn't matter. No, that's not necessarily the case. That just means you were not able to detect an effect. So there could be an effect, but it's just hard to tell, maybe because two things are collinear, right? So it's hard to see which of these is actually causing or somehow contributing to the outcome. Similarly, if you do inference and you say that something was significantly different, therefore it really matters, not necessarily the case. You could have a very, very small effect that is very significant if you just have enough data. So that doesn't mean that it actually makes any substantial difference. Like if I change this thing, even from its smallest value to its largest value, that might not make any meaningful difference in the outcome. The outcome might stay basically the same. It just means that there is going to be some very small change in the outcome, and I can detect what that is, but it doesn't mean that it's a clinically meaningful difference, right? And then same thing for model selection and inference. If you start messing with the model, doing stepwise regression, things like that, that just kills all of your confidence intervals, because you're doing multiple testing and you're not accounting for that. You cannot believe the p-values or the confidence intervals after you've done the selection. All of that stuff that we talked about last week. Same thing applies if you're doing logistic regression, linear regression. It actually doesn't matter. Some quick things that you should just be aware of as well. If you are some synonyms here, right? If you're doing logistic regression without additional predictors, if you just have one binary predictor and the binary outcome, that's the same as doing a chi-squared test. All right. Or people will just call that unadjusted analysis of a binary exposure. And then if you start adding things in, that is sometimes called a adjusted analysis. All right, so here's a quick problem. We ran this logistic regression. This is the COVID testing data. We're trying to ascertain the probability of having a positive COVID test. And as predictors, we're using gender, the day of the pandemic. So this is counting like day 0, whenever they decided that the pandemic was declared. Day 0, day 1, day 2, so on and so forth. When did this test occur? And the person's age who's taking the test. And so let's say we run this. And these are the results that we get, okay? And these are the robust standard errors, okay? We have these coefficients, and these are the p-values. So given these results, I just want you to think about if these are fair conclusions, which one of them are and which of them are not. And think about also why somebody might conclude this given these results. What are they looking at? Okay, so first one, for all days in the pandemic and for any age group, males had fewer positive COVID tests. So here the person who's making that claim is probably looking at this, right? This coefficient here, and saying that's negative. And in the kind of standard interpretation of this coefficient, this is, let's go back actually to that slide. What we're looking at is something like this, right? So this kind of like conditional log odds, and they're saying that, okay, this thing is negative, which means that basically the probability that y equals 1 for males, I think. Okay, yeah, the probability of a positive test for a male is lower in any bucket, right? So it's conditional. So in any bucket of the population, which here is x2, this being negative means that the probability of a COVID test being positive is lower if you're a male than it is if you're not a male. That's the one interpretation of the coefficient. And the problem with this, that's true. There's nothing false about that. The problem is that this is now inferring something about the actual data from the model. So just because the model thinks that this conditional odds ratio holds, right? This is the model's interpretation of the truth. That does not mean that is actually the truth. So I can find you in this data set a day and an age group where males actually had more positive COVID tests. That doesn't mean that the coefficient is wrong. The coefficient is just kind of averaging, right, over different days and age groups. So just because this is negative doesn't mean that this is actually, even though it's conditioned, it doesn't mean that this is actually the truth, and that this model actually represents the true data generating process. If it did, then yes, this would be a true statement. But you can just look at the data and see that this is actually false. For any fixed values of gender and pandemic day, each additional year of age increases the predicted log odds of a positive test by about 0.017. So here we're looking at this coefficient here, and this interpretation is completely correct. So this is just saying that this coefficient is corresponding to the predicted log odds of the outcome. So if I increase this coefficient, if I increase the value of this predictor by a little bit, here's how my predictions would change. Nothing wrong with that, because you're clearly saying this. What's changing here are the predicted log odds, not the true log odds. Okay. Moreover, you're correctly saying that this is for fixed gender and fixed pandemic day. And then, okay, the last one here, the population rate of positive COVID tests decreased over time in the recorded period. So here you're probably looking at pandemic day, right? The fact that this has a negative coefficient for pandemic day kind of would make you think that, okay, over time we're having fewer and fewer COVID tests that are positive. This is not necessarily the case. Again, here you're kind of extrapolating from this is what the model thinks to this is what actually happened in reality. So a better way to answer this question would actually just be to look at the rate of positive tests in one period of time versus another period of time. And here this statement is not even really clear. What do you mean decreased over time? Do you mean that there's period A, period B, and the rate was lower in period A over period B? Because this coefficient could be negative, for example, if the rate of tests were high and then it dropped a lot and then it kind of went up again, right? That could still have a negative coefficient. Moreover, this coefficient is conditional. So this coefficient is kind of reflecting the what the model thinks is happening for a fixed age group and for a fixed gender group. And it could very well be that for many age and gender groups, or for the population as a whole, the rate of positive COVID tests is increasing, even though for any given subpopulation, it's the model's perspective, it's decreasing. So if you remember, we talked about Simpson's paradox. That could be going here on here. So there's a lot of things actually wrong with this statement. You cannot just say the population rate of positive coefficients increased just by looking at this this coefficient here, because one, this is conditional, and two, it's basically just the model's opinion. It doesn't really reflect reality. So if you found that kind of difficult or hard to wrap your head around, that's not weird, or it's not you haven't done a bad job understanding the material. It's because this stuff is really subtle, and the message is just don't do it. All right, so don't jump to these conclusions. You can say a lot less than people think you can based on these coefficients. Really, the only thing you can say is this super concrete thing that is like just directly from the definition of the coefficient. This statement here, right? Beta is the amount that the predicted log odds increases given a 1 unit increase in x. That's it. You really can't say basically anything more than that. And this only pertains to the predicted log odds. And what happens when 1 unit increase in this, and I should put here conditional, fixing everything else. So here this is only with one predictor, but if I had other stuff, this would be with other stuff fixed, held constant. And other things that are not in the model allowed to vary. So if you rewatch the section on linear regression when we talked about that, how the estimate is really changing depending on what you have in the model. So again, if it's difficult, I mean, don't worry too much about the specifics. I just want to scare you away from doing this at all, because it's probably wrong. And you should have red flags when you see this kind of stuff in papers where people just start interpreting coefficients willy-nilly, because there's so many places where you can go wrong by doing this, that it's difficult to even teach, because there's so many ways you can make a mistake. It's easier to just say here's the right way to do it. Here's kind of what you should be focusing on. At the end of the day, if you're looking at tables of coefficients, it's all just vibes. If you want to report it that way and you say this is kind of our feel for the data, use it to generate hypotheses, that's totally fine, but it's simply not rigorous.